Hi everyone, today I would like to talk about Newton method for convex function, right? So in the last video I talked about nonlinear least square, and in a sense this is an extension to that video because we're going to use a Newton method, but it's very similar to the Gauss-Newton or even the Newton-Raphson method. This is only for a convex function, and you'll see that actually there is only a small modification to the previous techniques, right? So if you have not already watched the other video about nonlinear least square method, I will put a link in the description. Please go ahead and watch that one first before watching this. A lot of ideas actually are exactly the same. Okay, so let's start. Before talking about the Newton method for convex function, it's important to have a good grasp on a concept of gradient and also Hessian. So assume you have a scalar value function g of x. What I mean by scalar value means that g of x is a function from Rn to R, right? What I mean by that means that x is n-dimensional. So x is x1, x2, all the way to xn. So this is the domain of a function, and this is the codomain, right? R. So the values I can obtain. Okay. In that case, the gradient of g of x, right, is defined as a column vector, has the same dimension as the argument inside g of x, right? Like argument inside g, which is x here. So here x is n by 1, so gradient will be n by 1 as well, right? And it's defined as a partial derivative of g of x with respect to each component, respect to x1, then respect to x2, all the way respect to xn. Okay, good. Now, the next concept, which is very important, is the concept of Hessian, which is a matrix of second derivative. Now, it's important to know that Hessian is a square matrix. It's n by n, right? Where n is a dimension of x. X is n by 1, right? So, in a sense, the first row is that the partial derivative of second partial derivative of x, right? The second derivative of g of x respect to x1. Then, so this row, you can consider it to be for x1, this row. And then this row is going to be for xn. So this is going to be respect to x1. You twice will take it with respect to x1. Here you first take it with respect to x1 and then take it with respect to x2. Here you first take it with respect to x1, then you take it with respect to xn. Right? Now it's very interesting. If I actually fill out this matrix a little bit more, for example, here I get partial derivative of second derivative of g of x respect to x2 first, then x1. So these two are the same, right? And then this one, of course, is going to be respect to x2 twice. And then this one is going to be respect to x2 and then respect to xn, right? So you see these two are the same. The element of 1, 2 and 2, 1 are the same. So this matrix is symmetric. This is a symmetric matrix. It's very important to know that. So Hessian is a symmetric matrix. So this is called Hessian. Hessian is always symmetric. And this is called gradient. Okay, good. Now let's talk about properties of Hessian and gradient. So if you define a affine function, if g of x is A transpose x plus b, right? Then the gradient of g of x is A. How do we know this? You see, this is a scalar function, right? Gradient is a column vector. If I know it's either A transpose or A, but remember, A is a column vector. A transpose is a row vector, so it's going to be A, right? And the second derivative, of course, is 0 respect to x, because gradient of A respect to x is 0, so it's going to be 0. Okay, good. Now, if you have a quadratic function, x transpose px, remember this is a quadratic in x, plus q transpose x plus r, right? Where p is symmetric. In that case, the gradient of g of x is going to be 2p of x plus q, right? If p was not symmetric, this would be p transpose plus p times x plus q, right? And the Hessian is going to be 2p, right? So the Hessian is going to be here 2p. If you take it with respect to x one more time, you take a gradient one more time, you get 2p. Okay, good. Now sum of two functions. If g of x is equal to g1 of x plus g2 of x, Then the gradient of g of x as sum of the gradients, exactly like a properties of the derivative, right? So you take gradient of g of x, g1 of x first, plus gradient of g2 of x. The same thing is for the Hessian, because the Hessian is nothing but applying gradient twice, right? You can think of it like that. You can think of it actually like this, right? Or you can actually write the definition of Hessian and prove this stuff. Okay, good. So a scalar multiplication also is easy. If g of x is equal to alpha f of x, then the gradient of g of x is equal to alpha gradient of f of x, and Hessian of g of x is equal to alpha Hessian of f of x. Okay, yeah, in a sense, you multiply the alpha by gradient f of x or alpha by Hessian of x, right? To get the gradient and Hessian of the g of x. Okay. Now this is very important property, the fifth one, the composition with affine function. So if g of x is f of c of x plus d, right, where c of x plus d, is it this c of x plus d? This is gonna be a vector, so this is like a affine, right? And c is n by n and d is n by 1. Remember, if c is n by n and d is n by 1, the cx plus d is gotta be n by 1. So now argument inside f is n by 1. So gradient of g of x is gonna be gradient of g of x, or gradient not g of x, gradient of f of x is gonna be this gradient of this. It's gonna be m by 1. This is gonna be m by 1, right? Okay, so gradient of g of x, let's see. So g of x, the x is still n by 1. The gradient of g of x is still gonna be n by 1, right? So we know that it's gonna be either c here or c transpose times gradient of f of c of x plus c. Well, wait, this is n by 1. If I write c, c is only n by n. This doesn't make sense. So it's a check that you can have. So it's gotta be c transpose. N by n times n by 1 is gonna be n by 1. And then if you take a gradient of or Hessian of g of x, you get c transpose times this should be Hessian of f of x, f of cx plus c times c. Okay, so that's a actually pretty interesting property of the Hessian and gradient when you composite the function with the affine function. Okay, this can be used sometimes to simplify your expression, right? To calculate the Hessian and gradient. Okay, now let's talk about the optimality condition. So first, let's talk about the convex function. Convex function have numerous applications in real world, and that's why they are studied, and they are studied actually a lot in the literature because they actually have very interesting properties, right? So right now we're going to look at some of them. A function g is convex if this Hessian is positive semi-definite everywhere, meaning the second derivative of the function is positive definite, positive semi-definite everywhere. So why is that important to study the convex function? If g is a convex function, then the x star is minimum if and only if the gradient of g star, g of x star is equal to 0, right? So it's if and only if, it means that x star is minimum. This means gradient of g of x star is 0. And if gradient of g of x star is 0, then x star is minimum. This is quite important because this is not necessarily the case for non-convex function. We're going to see that in a minute, right? So remember this one. And also if the function g is convex, right? If x star is minimum, then it's going to be a global minimum. So if you say local optimality is a global optimality, right? This is a very interesting property of convex function. Now, what if g is not convex? Means that the Hessian is not positive semi-definite everywhere, right? Then it's not sufficient, as I wrote here, to have the gradient of g of x star to be 0. This is not sufficient to have that. Why? Because the point can be local minima or saddle point or local maxima as well, right? So, for example, if you consider the case of 1D, right? it's very important to have some intuition here. If you consider this function, x2, right? So n, let me just y equal to x2. So x is 1D right now, one dimensional, so n dimensional. So the second derivative, or Hessian in this case, is going to be 2, right? So for example, you see that the Hessian here is, for example, positive definite everywhere, right? So it's definitely positive semi-definite. So this one, the minimum point is here. So this is a local minimum, but at the same time also is a global optima, right? But now if you consider, so this one is the convex everywhere, right? Because the second derivative is equal to 2 at any point. But now if you assume you have a function like this, right? So this function is not convex, right? So here let me just make it more interesting here. Right, there you go. So here the local minima is not actually the global minima. Because if you consider this point is A, this point is B, point A, the value of point A, or the value of function, let's say f of A, is actually smaller than f of B, right? So the local minima is not actually the global minima, right? But the point that I want to try to stress here is this, that the value of the derivative, the gradient at this point is 0, right? Okay, but also at this point is 0. From the calculus, we know that local minima, local maxima, right? So if the function is not convex, when the gradient is 0, it can be local minima, it can be local maxima, or worse, it can be a saddle point. So remember this property is only for convex function. Okay, good. Now, however, to help us more, we have some sort of local optimality conditions, right? So what is this local optimality condition? First, we have a necessary condition. So this is for non-convex function, non-convex. If x star is locally optimum, this is a necessary condition, right? Then the gradient of g of x star is equal to 0, and the Hessian of g of x star is positive semi-definite. In that case, the point x star is locally optimum, right? So this is a necessary condition. This is necessary. So if the point is locally optimal, then this is the case. Right? It's quite important. So it's a necessary condition for the point to be a local optimum, right? For the function g that is not convex. This is a necessary condition. Now we have a sufficient condition as well. Means that if the gradient of g of x star is equal to 0 and the Hessian is positive definite, then it's sufficient to say that this point is local minima or locally optimal, right? So these are the two local optimality condition that we have when g of x is not a convex function, okay? But here in this video, we want to stress on solving a convex optimization problem through the Newton method. So these 2 points are good to remember for non-convex actually function, okay? So here our job actually is much easier because we are actually need to focus on this point here, okay? So what is a Newton method for convex function? It's very similar to Gauss-Newton. Why is that? See, since g of x is convex, right? We assume that we are talking about the Newton method for convex function. So if g of x is convex, then optimal point happens when the gradient of g of x is equal to 0 at the point x equal to x star, right? So when the gradient of the function at that point is 0, then we are getting a local minima, right? Okay, we just proved that. This is if and only if a statement. We just talk about that. So in a sense, I can apply the Gauss-Newton and or any other method that we talked about in the last video to this set of nonlinear equation. Because if g of x is nonlinear function, then so as gradient of this will give us a set of nonlinear equation. Remember, gradient is actually a column vector. So it gives us set of. So and it gives us set of nonlinear equations, right? Okay. So this nonlinear equation can be solved with any method. But let's say, for example, if you want to solve it using Newton method, right? Or Gauss-Newton method. In that case, you see, for example, when we had, let's say here, for example, we have x is n-dimensional, x is n by 1. So the gradient, this one, also is going to be n by 1. So we have n equation and n unknown. Therefore, that matrix D that we were talking about, that Jacobian matrix, is going to be n by 1. So if it has a linearly independent column, then it's going to be invertible, right? So in a sense, we are going to go ahead and replace the f of x that we had in the Gauss-Newton update equation. Let me remind you what I'm talking about here. We had some sort of xk plus 1. Here I'm putting the subscript here actually, right? D of f of x of k, right? Inverse, remember we had these, and times actually f of x of k, something like that, right? So in a sense, now this f of x of k, we're going to replace it by gradient of f of x of k, because we are solving system equation for gradient of that. So that one is going to be a second derivative, and that's where the Hessian comes in, right? And then this f of x of k is going to be like a gradient of x of k, because we are applying to this function now. This is our new function, okay? So now it's a very interesting problem occurs that we are actually trying to invert this quantity, this matrix. But wait, I said if g of x is convex, then the Hessian is positive semi-definite everywhere. We talk about, remember the video, we talked about the positive definite matrices. If a matrix is positive definite, it has all the eigenvalues are positive. But if a matrix is positive semi-definite, it can have a zero eigenvalue as well. So here for this Newton method for convex function, we assume that here for this method, we assume that Hessian is positive definite. Okay, very good. So when you see this update equation, this is the assumption. Otherwise, the Hessian would not be invertible because there can be a zero eigenvalue, right? So it's strictly convex. We kind of assume that it's strictly convex, and the Hessian is always positive definite. Okay, good. So that's gonna be the update equation for that. Now, how do we solve this one though? This Hessian, inverse of this Hessian is not really a nice thing to do. What is going on really is to use the tools that we have learned thus far. I'm gonna talk about some of them right now. I'm gonna paste that one here. So let's see. Let's forget about this. So usually the way we do that is we set this one equal to, let's say, y, right? So if you multiply both sides by the Hessian of g of x of k, you get this. You get Hessian of g of x of k times y is equal to this. So you're going to go ahead and solve this system of equation instead of inverting the Hessian, right? And after you find the solution of that, the solution of that is, for example, let's say you solve this one with a negative sign, right? After you find that, the solution is, let's say, is y, right? Then you're going to go ahead and say xk plus 1 is equal to xk plus y, right? Whichever, if you don't want to include the negative there, then it's going to be negative y. And you're going to subtract the y from the xk. So that's what we do that. We don't usually want to invert the matrix, okay? It has a huge complexity. That's one thing. The second thing I want to talk about that is that if you assume this Hessian for a strictly convex function, because you want it to be invertible, to be positive definite matrix, right? If this is a positive definite matrix, so I will write it down here. If this one is positive definite matrix, then of course, then we can use Cholesky factorization. Then we can use Cholesky factorization. I will call this one 1, I will call this one 2. To solve 2, right? And I talked about Cholesky in the previous videos, right? So we can actually have this option to solve this equation as well. So once we write this equation, this update, then we have many ways actually to solve that one. So that's it about the Newton method for a convex function. Okay, so thank you so much for listening.